Thank you, Professor Livescu, for inviting me to talk about geomechanics for geothermal energy. So I know that during this class, you guys have learned a lot about geothermal energy. And today, I'd like to add a component about what is the importance of geomechanics and geothermal energy. So you have learned so far about how geothermal energy works, the facilities, how it works today. We'll see that there are some challenges in taking this into future designs, particularly for very deep conditions and for large-scale systems that will have enough power, say, to power a city or to power your cars. And that's where the challenge is. You know these advantages. The geothermal is always on, very small CO2 footprint, and is really something that is going to take a share of the energy in the future. There are some disadvantages, however, that we have to be aware and we have to consider whenever we design these systems. And particularly today for geomechanics, we're going to talk about what might be the cause for induced seismicity, how we can avoid that, and also how we put geomechanics into consideration when designing these systems. Basically, as we're going to see, when we have a geothermal system, we're going to change the pore pressure, we're going to change the temperature, some other times by injecting a fluid which is not native to the reservoir. You can also change the geochemical equilibrium and have scaling and issues like that. We're not going to talk about that today. We're going to talk mostly about the geomechanics. Okay, there are several challenges related to geomechanics for these deep and massive geothermal systems. The first one is drilling. So drilling some of these wells at very high temperature, it's very challenging. Probably just drilling a straight wellbore, vertical, not so much. But if you have to steer a wellbore in a very complex pattern, like, for example, some companies are proposing to have this sort of like radiator-shaped wellbores that they meet at 8 kilometers of measured depth in the wellbore. Well, that can be challenging, right? So steering the well is challenging, and also the cost involved in drilling the rock, and we're going to see why, is very challenging too. As we were saying before, induced seismicity is also a big concern. For example, in Korea, after 2 years of operation, they saw a major earthquake close to a geothermal power plant, and that stopped everything. We don't want that to happen. In some other places, however, it appears that lowering the temperature in a reservoir can help release the elastic energy of tectonic plates. Basically, if you have like two plates coming together and adding energy to the rock in the form of strain energy, and if that gets released more or less continuously towards what we're going to see is called thermal distressing, that can be helpful too. So we need to know the entire picture of how geomechanics is going to affect geothermal energy. And very importantly too, going from conventional systems that might be relatively small and in particular locations, like we were saying before, an example of California or Iceland, as we go to geothermal everywhere and to geothermal also maybe in sedimentary basins, we need to know also how geomechanics is going to affect that. If we need to create hydraulic fractures, how those hydraulic fractures are going to be, and how flowing a fluid through a system like that is going to affect the performance of the system. And this is the case I was mentioning before. Also, to increase power, we need more surface area. More surface area, like with fractures, or also with having more wellbores. But this is challenging. Creating fractures is not straightforward. Geometry is not straightforward. And drilling so many wells also, that's quite costly. Okay, so a few questions that we're going to try to answer in this short lecture is how difficult it is to drill those wells? Is fracturing necessary? Will there be any induced seismicity? What are the best practices for geothermal reservoir engineering? We can also talk about geothermal reservoir engineering because that's going to change the performance of your reservoir, similar to oil and gas. And also, how can geomechanics affect the installed power capacity? That link may be not straightforward, but we were saying before in the case of Korea that after 2 years, everything ended. So that's, recovery factor 0 after 2 years. All right. So in order to do this, we're going to do a very, very quick review about geomechanics and about structural geology. So by the way, guys, feel free to stop me at any time if you have any question, okay? So this is not a seminar, this is a lecture, so I invite you to participate. All right. All of you guys are familiar with pore pressure. What is a typical gradient of pressure in a subsurface? Can anyone tell me?
0.433 psi.
Very well. That's under normally pressure conditions. Your gradient will be around that, 0.43, 0.44 psi per foot. What is a typical gradient for total vertical stress? 1 psi per foot. Very well. That's for typical weight of the rock. What is a typical temperature gradient?
1 degree per 100 feet.
More or less, yeah, you could say that too. I see that many of you are familiar with this. I don't know if you also know the variations of horizontal stresses with depth, which is what just popped up there in the screen. So these stresses are very important because horizontal stresses are going to tell us in which direction hydraulic fractures are going to propagate. They're going to tell us in which direction we need to drill our horizontal wellbores, and they also control which type and orientation of fractures are going to reactivate in the subsurface. All right, let's make a block diagram of that. So we can look at these stresses and now get to see the 3 different stresses that we usually have in the subsurface: vertical and horizontal. It's very important also that we know the concept of effective stress, which is the difference between total stress and pore pressure. That's what really makes a rock fail, and also that's what changes the porosity. It's not the total stress, it's not the total depth, it's really the effective stress. And that's a lot easier to see in a more circle diagram, where here we have our 3 principal stresses, assuming vertical stress is the principal stress, and we have all the possible state of stresses for this block and fractures that might be within that block. In situ conditions, they usually will be close or far from failure. That depends where in the particular location in which you are. But what we do not want to do is to change the stresses so that we go into failure. Well, let me rephrase that. Sometimes we do want to change that. For example, when we do hydraulic fracturing, we want to change the stress so it fails in tension and we create a hydraulic fracture. And some other times we might want a reactivation of fractures in shear, like for example in hydraulic fracturing too. So we want some of these to get past the shear failure. But some other times we don't want that. So we want to know, we should know how we get to those conditions when we want it and how we avoid that when we don't want it. For example, fault reactivation is a case of these stresses going past the shear failure limit. All right, so this is a very fast review of geomechanics. Do you have any questions, guys? If you haven't taken my class in geomechanics, I encourage you to do so. I have an undergrad class and also an advanced geomechanics class, in which we go in a lot more detail about these concepts. All right, so geomechanics, next thing, very important too, structural geology. So how do stresses, faults, unfold the earth crust? That depends on geomechanics, and that's what makes a rock look like as they do in the subsurface and also on surface. And that's mostly driven by plate tectonics. The plates move and they smash the rocks as the plates converge, or you might have an extensional regime where the air crust extends, and that's going to change the value of the horizontal stresses. We're going to have places which are called under normal faulting regime or extensional regime, in which the least principal stress is horizontal. We might have other places, however, where plates converge, like for example here or over here, usually associated with big mountains, where the plates are converging and there is a very high horizontal stress. Sometimes the two horizontal stresses are larger than the vertical stress. And as we're going to see later on, that's super important also for geothermal energy. So when the rock fails, mostly fails in what is called an open mode failure. This is an example of a dike. This is a hydraulic fracture, which is natural. In this case, if I remember correctly, this is a magmatic dike. So it's lava that opens the rock and creates a large hydraulic fracture. This is failure, what's called in open mode, and it's always perpendicular to the least principal stress. That's why we were saying before that our hydraulic fractures, which are also type of open mode fractures, are expected to be ideally perpendicular to the least principal stress. Under the normal faulting and strike slip conditions, the least principal stress is horizontal and fractures are vertical. However, under reverse faulting, these fractures are going to be horizontal. In geology, that's what are called seals. That's open mode failure. We also have shear failure. This is what creates faults. And also this is how faults reactivate. And depending on the stress regime, they could be normal, reverse, or strike slip too. And these faults are present everywhere. Sometimes you have smaller fractures or smaller open mode fractures, but they are everywhere. And we need to know where those are in our geothermal reservoirs. Okay, very fast review of solid mechanics. You remember, guys, the Hooke's law, right? If you extend the Hooke's law to 3 dimensions by using the Young modulus and the Poisson ratio, you get these equations over here, which are the elasticity equations that relate stresses and strain through the elastic parameters. For isotropic solids, these are the Lamé parameters, and which are also expressed as a function of Young modulus and Poisson ratio, and you have just 2 independent constants. If you want to solve the general problem of continuum mechanics, you need to add to this what are called the equilibrium equations and the kinematic equations that relate displacement and strains. You put that together with your constitutive equation, which is the one I have on the left, and you get this equation, which is a differential equation, which is called the Navier equation. That is what is built up in the geomechanics module of your reservoir simulation software or any continuum mechanics software. Is this equation over here. It may be a little bit different depending on the constitutive equation and the kinematic rules, but basically is that the differential equation that allows you to solve for displacement and tell what is the field of stresses in a particular location. Let's see some typical Young moduli, and let's see, how this is going to be important for the case of geothermal energy. As you can see in this plot, the Young modulus varies over several orders of magnitude, like going from sediment and soil from 0.1 gigapascal to 100 gigapascals. And the tougher rocks, the stiffer rocks, happen to be the igneous rocks, metamorphic rocks, where many of the geothermal reservoirs are or are targeted to be. So these are very stiff rocks, and that's going to make a difference, as we're going to see later on. Let's now extend the mechanics to thermoelasticity. I think you guys are all familiar with the concept of thermal dilation, right? So materials, most materials, when you increase the temperature, they dilate. That's what is called a thermal strain, and it's quantified by the thermal expansion coefficient that tells you what is the variation in length related to the original length for a change of temperature, in this case, at constant pressure. So typical values of this thermal expansion coefficient for rocks are in the order of 10 to the minus 5 to 10 to the minus 6. 1 over degree centigrade or Kelvin is the same. So for example, if you were to change the rock significantly, as you might do in these geothermal projects, of 100 degrees, your strains will be in the order of 1,000th or 0.1 thousandths or 1/10,000th, which seems relatively small, but it is not. And we're going to see the reason why. Let's extend this example now to conditions in which we don't let this rock to expand in the either on the bottom or on the top, so in the vertical direction. So if you somehow restrict the displacement and increase the temperature now, the rock is not going to expand in the vertical direction, but instead is going to create what is called a thermal stress. How much is that thermal stress? Well, that can be predicted by this theory of thermoelasticity, where now we have the thermal dilation coefficient in it, and these are our stresses. And also we have here K, which is the bulk modulus. And for typical values of the thermal expansion coefficient, and let's say a change of temperature of 100 degrees C, for a rock with a bulk modulus of 10 gigapascal, we'll get a thermal stress of 30 megapascals, which is around 4,400 PSI. Is that large? Too small? What do you think, guys? That's pretty large, right? So these stresses are non-negligible. Let's see the case of a soil, for example. If we have a system which is closer to surface, with a much smaller bulk modulus or a much softer rock, sometimes the rock doesn't have to be softer, but if you have many fractures in it, the fractures make the rock more compliant as a whole. So in this case, if we lower the bulk modulus 100 times, our change now is 0.3 MPa or 44 PSI, which is not that much. What this is telling us is that this thermal stress is going to vary, and it's going to be usually larger in deeper locations with stiffer rocks. And this is the case when we increase the temperature. You could also decrease the temperature, and it's the same thing, but now you will have a reduction of stress. And that's what is called thermal distressing. And basically, in geothermal systems, we're lowering the temperature, so we're going to have a reduction of stress. Let me show this cool example that allows you to see that directly. Here, what we have is an acrylic block, and liquid nitrogen is being injected in this sort of borehole. And because of the sharp decrease in temperature around the wellbore, what you have are tensile-driven fractures. Notice how those fractures initiate at the wellbore and then propagate. And this is also a very nice example about how multiple fractures growing together can interact with each other. That's something which is called fracture interaction or fracture interference. And this is a result of thermal distressing. So in this case, the stress is getting so low in this direction along the wellbore that is cracking this material, which in this case is acrylic. And the same thing can happen with rocks. For example, these are basalt columns in Iceland in which the fractures that you see are created by thermal distressing. Basically, this basalt that sometimes crystallized as a slab, and then temperature changed, temperature reduced with time, so that there was an even distribution of the temperatures and the strains in the two directions, so that there is no preferential direction for a tensile fracture to be created. So it creates in all possible directions, and the least energy configuration is this one, with these hexagonal patterns, in which all of these are tensile fractures. So these thermal stresses can be severe enough that they can fracture the rock in tension, and as we're going to see also, they can reactivate fractures in shear. So how do you solve these problems now with mechanics and changes of temperature and changes of strain? Well, you can write this equation similar to what we saw before for the Navier equation. You can extend that for temperature, and then you can also solve for changes of temperature, so that, for example, in this numerical simulation, you can calculate what is the change of stress due to a change of temperature near a wellbore. This is also very well known in drilling. If you drill with a cold fluid, will the fracture gradient be the same, higher or lower than drilling with a fluid that has the same temperature of the formation? Okay, well, Mohammed says higher pressure gradient drilling with cold fluids. Okay, and anyone else, any other opinion?
I think the window would narrow because the thermal distress.
Yes, that's what's going to happen. The thermal distressing will lower the stresses around the wellbore and lower the fracture gradient, making the window narrow. So that's what is going to happen. So if you want to solve that problem for a wellbore, this is what you do. And in general, for any system, including continuum mechanics and thermoelasticity, this is what you do. I'm not going to go in detail. Again, if you want to take my advanced geomechanics class, then we talk about that too. However, notice that so far we just have considered rock as solid. Actually, rocks are a little bit more complex than that. You have also porosity, you have fracture porosity, you have matrix porosity. In many cases, in order to be accurate with your predictions, you have to use what is called the theory of thermoporoelasticity. So now we have change of stresses, we have changes of pore pressure, and also we have changes of temperature in time. And you can extend your equations in order to predict changes of pressure in space and in time, also changes of temperature in space and in time, and couple those two together. So I'm not gonna go in detail over this theory. If you're interested about this, I recommend that you read the book from Alex Cheng, very nice book about pore elasticity. But what I'm going to tell you now is that there are some funny things that occur here when you start considering the presence of a fluid. Because the thermal expansion coefficient of fluids, and we're talking mostly about water, is generally higher than the thermal expansion coefficient for minerals or for rock. What that means is that if you have a rock filled with water and you heat it up, and don't consider now the change of phase by going into, say, vapor. But if you just heat it up, the fluid is going to expand more than the rock. And if the fluid expands more than the rock, and you don't let the fluid get out of the rock, either because you seal the rock around or because the permeability of your rock is very low, then you're going to generate internal pore pressure. And that internal pore pressure can also fracture your rock. So putting now the fluid inside and considering all the coupled interaction between fluids and the rock actually leads to some phenomena that you might not predict if you consider the rock just as a solid. Yeah.
So will a rock also fracture due to de-stressing faster with fluid?
Okay, so not quite. So if you de-stress the rock, if you lower the temperature, the fluid, the water is going to shrink more than the solid, and that will actually increase the effective stresses in the rock, and that may or not make it fail depending on the horizontal stresses and in which direction you keep one of the stresses constant. That's what we're going to see later, but it does have an effect. It does have an effect. All right, so let's see. One more thing about mechanics before we go to the applications. When we talk about elasticity, deformation, stress, strain, usually we're talking about the relationship between stress and strain. But rocks also fail, also go through permanent deformation. And getting to know which type of failure we're going to have is very important. Because, for example, brittle rocks, when they fail, they release the energy instantly. That's what, for example, creates or emits a lot of seismic energy in an earthquake. But you might have some other materials which might never fail, like fail in the sense of having a sharp decrease of stress. These are what are called strain hardening materials, or you can have some other materials which are called like perfect plastic that you get to a maximum, and then the materials just keep that stress more or less constant. And that has a lot of impact, again, on the emission of energy, which in this case, for rocks, the most relevant one is through the seismic moment. And temperature plays a big role on that too. At higher temperatures, rock tend to go from behaving from a brittle manner, failing very, very quickly, through to failing in a more ductile manner. So this is also very important for drilling. If you wanted to drill a very deep wellbore, you also have to consider this type of phenomenon. All right. Any question? I think we're doing good with time. Also, we're going to have time at the end, I think, for questions. Just closing the loop on rock failure and coming back to the Moore circle. For example, if you were interested in drilling, you really have to fail the rock at the matrix level. And that is going to involve shear failure and tensile failure. And that's going to be the Moore circle going into either this red line or the green line. And the bad news, we could say in this case for geothermal, is that these rocks, igneous rocks, metamorphic rocks, tend to be quite strong. They are not only stiff, but they are also strong. Those are two different things. One thing is stiffness, another thing is strength. These rocks are stiff and strong, not only in tensile failure, but also in shear strength. Basalts, granite are at the top of what we can get for a rock. So the rate of penetration, for example, in a wellbore is not going to be the same in a loosely cemented or an unconsolidated sand somewhere over here than all the way over there. That's going to make a big change. And I'm not going to talk much about this. It's not my expertise either, but there are many people working in drilling, trying to come up with novel techniques to lower the cost of drilling, because these rocks are very strong, and lowering the cost of drilling is really going to make a difference in the future. All right, let's talk about geothermal reservoirs and how we can predict the stress path of a geothermal reservoir, and let's see how geomechanics plays a role in this. So this is an example from the fourth side. Basically here you have two wellbores, and here it's planned to have hydraulic fractures that will connect those two in order to produce heat out of here. All right, how do we simulate this? We could use simplified analytical models, like for example, this is what is called the uniaxial strain model. It's just basically a point solution. It's very limited, but gives you an idea about what might be going on in a particular location. You can also have simplifications, analytical simplifications. For example, consider an entire reservoir as an ellipsoid, and working, with Fourier transforms, spin functions, and things like that to predict what is going to be the change around the reservoir. Or we could do numerical simulations, and there are some phenomena that can only be captured considering or doing numerical simulation to account for complex boundary conditions and how properties change and variables change as a function of time. So we're going to talk about examples of these two. Before we get started, I just want to bring to your attention that what we're going to try to do is try to predict what is the change of stress in a given location in a reservoir because of a change of temperature. That's what we're going to try to do. And we're going to try to predict how that change of temperature can change the state of stress and lead the in situ conditions to mostly shear failure. That means past this shear failure line and going in this region. And we're going to talk, I'm not going to put too much emphasis on this because there's not much time to explain about the undrained case, but that was going back to one question from the audience saying what is the effect of pore pressure in thermal distressing when you have low permeability. This is what is called the undrained condition. All right, so let's see an easy solution for this problem. What we're going to do is we're going to solve the one-dimensional strain analytical thermoelastic solution. Let's see when this case would apply. Imagine that you have a reservoir in which you are injecting a cold fluid. And we want to predict what is going to be the change of temperature in this formation, what's going to be the change of stress due to a change of temperature. In this case, actually, when I was working on this, I didn't develop this specifically for geothermal energy, but it's just for a change of temperature. And this also happens, for example, if you were to inject any fluid in a formation. Okay, so first of all, we get our constitutive equation that relates stresses, strain, and temperature. The second thing that we do is we assume the conditions or the boundary conditions that are relevant for this case. And in this case, what we're going to assume is that this entire reservoir changes temperature a given amount, and that everything more or less changes temperature at the same time. So there are no gradients of temperature. The result of that is going to be that there is not going to be a, let's say, more contraction near the wellbore than far from the wellbore. And the result of that is going to be the strain is going to be the same everywhere, horizontal strain. And actually, we can assume that that's going to be 0. So the rock, the only thing it's going to do is just going to contract in the vertical direction. And of course, we're assuming that everything on top of the reservoir is staying there. So the total vertical stress remains the same. We change the temperature, the rock contracts in the vertical direction, and in the horizontal direction, we have thermal distressing. And probably it's easier to imagine this like similar to those basalt columns. If you have an entire reservoir that is trying to shrink or because of temperature at the same time, if everything is trying to shrink, then there is no room for horizontal strains because everything tries to shrink at the same time. No one can shrink. And that results, instead of a thermal strain, a thermal stress, or in this case, a distress. That's why these horizontal strains are 0. So if we put this into the equations and we solve this equation over there, if these are 0, then the only one that's going to survive is the one, in this case, in direction 3, which is the vertical strain. We can work with equations, replace one in the other, and figure out what is going to be the change of horizontal stress. In this case, sigma 11, which is equal to sigma 22. Those are the two horizontal stresses. It's given by this equation here on the bottom. And then we can explore a little bit more, change the bulk modulus for its equivalent in terms of the Young modulus, the Poisson ratio. And finally, come up with an equation that tells us what is going to be the change of stress due to a change of temperature. And that's, as you can expect, proportional to the thermal dilation coefficient, proportional to the Young modulus of the rock. The stiffer the rock, the more thermal stress you're going to change, and also depends on the Poisson ratio. So if we lower the temperature, the horizontal stress is going to decrease. If you increase the temperature, the thermal stress is going to increase. Let's put some typical values for the thermal dilation coefficient, Young modulus, and Poisson ratio, and you get more or less that you're going to have about 0.1 MPa of a change of stress due for every degree of change of temperature. Let's multiply these times 100. Let's say a change of temperature of 100 C. That's going to give you 10 megapascals. 10 megapascals, how many PSI is that? For those of you used to field units. It's about 1500 PSI. So 1500 PSI, that's about 10 MPa. That's a large stress. That's a large stress, and these changes of stress can be quite large, and we have to account for that. So let's see a case, a real case. This is in California. This is a field which is called the Brawley field, and here you have the stresses: vertical stress, ZZ direction, horizontal stresses, XX, YY. What type of stress regime is this, guys, if the maximum stress is vertical? Normal, very well. All right, so let's see what happened over here. In this field, they observed that with production and injection, they started to see a significant increase in the rate of subsidence. And also, they started to see quite a bit of seismic activity. Actually, that's a little bit better seen in this plot here on the right. They started drilling, start operation, not much induced seismicity yet, but after some time, they see a big increase in seismicity, and they also see that this cluster of seismicity is mostly aligned with the pre-existing fault, a large fault. If you see this from the top, also this is the cloud of seismic activity. This is actually a vertical cross-section. These are the operations, and this is the depth of the wells. So in this case, most of the geothermal activity happened at about 1 kilometer of depth, but most of the seismicity or the higher magnitude seismicity came from a deeper location. So what happened over here? What they show in this paper is that this is caused by the changes of temperature. First of all, as we were saying before, if we have these boundary conditions in which we don't let the rock move in horizontal direction, but it just moves in the vertical direction, you want to have subsidence. This is thermal subsidence because the shrinkage of the rock. This is what they observe over here. And second, you have the thermal distressing. In this case, the thermal distressing, seen here in blue, is lowering the stress on the fault so that if you have less effective normal stress acting on the fault, you're going to have less strength in the fault because this is proportional to the friction coefficient, right? The more stress you have in the fault, normal stress, effective stress, the more shear the fault can take. Now, if you lower that stress, the fault is going to take less shear. If this fault takes less shear, it's going to say, well, I'm not taking this shear. Who else is going to take it? And in this case, the deeper fault was taking that shear. At some point, the fault say, well, I cannot take anymore. So it started to release quite a bit of seismicity, up to, if I remember correctly, a seismic moment of magnitude 5.4. So that's relatively large, right? So we have to be aware of all of these and how geomechanics can affect the design of these systems. In this case, I don't think that was a major risk in these particular locations, but in some other locations it might be. So this is very important to consider. So guys, I know this is a lot of plots over here. Do you have any question about this? That probably, I didn't explain so far. Yeah.
Was this like, what was the methodology of this field? Sedimentary or igneous? And it was like thermoelasticity of big.
Yeah. I don't remember, to be honest with you, for this particular field. But in this case, the de-stressing, what caused was like the de-stressing of the fault in one location and then loaded another part of the fault. So the de-stressing didn't like directly affect the fault here on top, but it just mostly sent stresses to the lower part. Yeah.
So there's the band strikes that show that excuse me. Do you know the change in stress regime is predominantly noticed in a certain type of fault as compared to another?
Well, we're going, I think, into one of the slides I have, but I'm going to tell you the answer shortly. Normal faulting will tend to reactivate more faults because what you change mostly is the horizontal stress. And since the minimum horizontal stress might be already close to the failure limit, changing that a little bit, it will be easier to reactivate those normal faults. The opposite would be, for example, reverse faulting, because your vertical stress is more or less constant, and then you are decreasing your horizontal stress, but those already are pretty high. So you might be actually getting some of these systems into safer conditions from the point of view of shear. Okay. Yes.
The vertical scale on the left plot is kilometers.
In which one? In this one?
The left one, yeah.
Yeah, this kilometers.
And it goes to 20 kilometers. So probably that's actually not a sedimentary basin, right? So deep.
No. I was thinking mostly on the top, on the geothermal field that goes just up to 1 kilometer.
Okay.
Yeah, I'm not sure what road was in this case.
Okay.
All right, okay, guys. I have almost, I think 10 more slides, so I think we're gonna make it on time. Okay, so how do we solve some of these complex problems? We do it with numerical simulation, similar to the case before. That was my case. It's a great paper, but I'd like to share also some of the work that we're doing. And in this case, we use the full thermoelastic numerical solution using the solver, which is called COMSOL. So here we solve for stresses, for pore pressure, for temperature, and all the equations coupled together to see how temperatures are going to affect the stresses, and again, pore pressure. Let's start with this example. A multi-well completion in which we have several injectors that are going horizontal and then going into a producer. We're going to simplify this model and we're going to make it 2D. So we're going to look at the vertical cross-section of the model and see how stresses are going to change around these wellbores as we change the temperature. So here we model the entire stack, but I'm just going to show the results near the wellbores. And this is the result. So increasing here in time, we go from 0 to 100 years, in which we stop the operation at 50 years. As a result of circulating the working fluid, as you might expect, temperature decreases around the wellbores. Pore pressure starts at the value which is, in this case, at this step, around 56 MPa, decreases with a decrease of temperature as a function of time. Why would this be? Remember, let me give you a hint. In many of these closed loop designs, the objective is to circulate the fluid without changing the pore pressure of the rock directly. So there is no interchange of fluid between the rock and the wellbore. So we're not changing the pore pressure by injecting fluid into the rock. Why would the pore pressure change? But the rock is so yeah, the rock is cooling, but
the pore spray,
the fluid is cooling faster, is at a higher rate than the rock, or the fluid is cooling more. No, let me rephrase that. The fluid is shrinking more than the rock, and that what causes is a decrease of the pressure. This is what we call the undrained condition. And this was this funny effect of the thermal dilation coefficient, expansion coefficient of the fluid, larger than the thermal dilation or coefficient of the rock. It's a few MPa, not that much, but it does change. And effective stresses change too, because of the thermal distressing. Now you have a change of the horizontal stress, and also you have the weight of the rock on top, which didn't change, right? What that's going to do is, imagine that you have a piece of rock in which the load on top remains constant, but you start decreasing the horizontal stress. What's going to happen in this case? If you keep this load constant, but you decrease the stress, you might fail your rock in shear, because this stress, vertical, is a lot larger than the horizontal. And this is actually what also we see in the simulations, that there are going to be regions in between the wellbore that go past the shear failure limit, in this case expressed with this equation, which is the maximum stress anisotropy. If you have any fractures in between these wellbores, and they are what are called ideally oriented to reactivate, in this case in normal faulting, they would reactivate. In terms of a stress path, this is what we see, that the least horizontal stress, in this case horizontal, decreases with time. The vertical stress increases. This is for a point here in the middle, and that takes the rock to failure. And in these two cases, we did two simulations, one with low permeability and another one with high permeability. And what we see is that depending on the permeability, the stress paths are different depending on these undrained or drained conditions, and also the time for achieving failure, it differs too. So with these simulations, we can actually also tell how long this particular geothermal design is going to last until the moment it starts inducing microseismicity. At the beginning, very likely nothing is going to happen, but if the rock is stressed enough, you might start seeing induce microseismicity because of the reactivation of fractures in regions which have a lot of shear. And very importantly too, if you were to consider induced seismicity or microseismicity as a limit for how much heat you can produce from these formations, you will have, for example, to stop your production at a given time. So the lower the temperature of the working fluid, in this case 110 degrees C, injecting in 200 C rock, the higher the power is going to be. That makes sense, right? But also, the shorter is going to be your time to achieve this induced microseismicity or reactivation of natural fractures, because you're cooling the rock faster. So if this happens to be a limit for your operation, that's something that you have to consider too. And answering your question before, it depends also where you start. If you're close to the limit of normal faulting, this is what is called the stress polygon, and tells you how close you are from shear failure and fault reactivation. If you are in normal faulting, this is actually the worst case. And if you lower the horizontal stress, you might reach this limit. If you are in strike slip or reverse faulting, you might have other conditions. For the normal faulting case, what we see is that the recovery factor, that we call the recovery factor, the amount of heat until you get a certain limit of reactivation in shear. And in this case, we set a very rigorous limit to 10% of the volume of the reservoir getting into shear. We calculate that these recovery factors are in the order of 10 to 20% of all the available heat that you can get from a reservoir, multiplying the volume of the reservoir times the heat capacity times the change of temperature between the initial temperature and the working fluid temperature. And if you were to be in a strike slip or reverse faulting, that changes. So if you were to analyze a geothermal field, it's very important also to get to know what are the stresses on those sites, because the geomechanical response is going to be different. I think this is the end for the closed loop. Any question about the closed loop? It might be, you know, for the closed loop that everything is solved, no problem of geomechanics at all. I don't think that's entirely true. So geomechanics is everywhere, and also is going to have a role in closed loop designs.
I have a question.
Let's go to the next one. Enhanced geothermal systems. All right. So now this is a little bit more challenging from the geomechanical point of view, and there are other things that we have to figure out. First of all is creating the fractures. Creating these fractures, connecting wellbores, it's not easy at all. the actual fracture geometry that's going to happen in the field is something very hard to predict. Sometimes we say, oh, this is going to be perpendicular to the least principal stress. But that's the ideal orientation. And sometimes it might not happen like that. In some of these rocks, also they have a significant number of natural fractures. The rock has a higher fracture toughness. All of that makes this a lot more complicated. In many of these places too, it's quite difficult to measure the in situ stresses, so you don't even know what the stresses are to begin with. So predicting fracture geometry is quite difficult. So if you want to learn more about hydraulic fracture geometry, I'm not going to tell you to take my class. Take Professor Sharma's class. So in Professor Sharma's class, you will learn a lot more about hydraulic fracture. And now I'd like to concentrate mostly on the reservoir engineering part of these systems. The whole idea here is to create more surface area. So our fluid takes more heat from the rock. However, there are some issues with that. And this is what is called thermal short circuiting. Basically, you start injecting a fluid, goes to the fractures, but what is the fluid going to do to the rock? And we're talking about the working fluid with a lower temperature than the rock. It's going to cool the rock, and cooling the rock is going to decrease the stress and also deform the rock. And it happens that in this fracture sometimes, imagine that this square now is the fracture. You can go from an initial time in which your streamlines are very nicely distributed along the fracture face, but as the rock starts to cool, of course it will cool a lot more between the injector and the producer. That cooling will open the fracture preferentially, and open the fracture is going to take more fluid. So eventually this is going to create a positive feedback mechanism in which all the fluid is just going to go through the center. This is what is called flow channeling. And this is not good, because now your fluid just goes directly from the injector to the producer. Another phenomenon is called plane channeling. And this is when you have more than one fracture. And in this case, mostly this is geometrical, but we're going to see that geomechanics also plays a role in this. But basically, your fluid goes into the injector, goes to the fracture, and then it doesn't go to the other fractures, but it just goes to one preferential fracture, and then it just goes through there, and then comes back to the producer. That's not good either. And those two are things that we want to avoid in a geothermal design. And those two depend on geomechanics too. All right, so what we did in this case is to model that numerically. Basically here now we have to model the fracture rock mass. We have to model the fractures, the compliance of the fractures, how they open when you de-stress them, and how they open after they lose contact between each other. And also we have to model the wellboss and the partition of the fluid in the fractures. So believe me, this is not easy. So my grad student, Matt McLean, has been working very hard on this. And but we have come up with very nice results that predict this flow challenge that we were referring before, and are comparable also with previous simulation results. So basically, what's going on here with the flow channeling? X-axis, we have time, and Y-axis, we have reservoir temperature. You start injecting, and this is just for one fracture, okay? You start injecting, and then the working fluid goes to the fracture, and then takes heat and gets produced at the other end. If you were to imagine that that fracture doesn't deform, and that stays with the same shape throughout the entire life of the reservoir, you will get this solution, which is called just the thermohydro solution, no mechanics. So, of course, you know, the working fluid temperature is going to decrease as a function of time, the same thing as in a wellbore in a closed loop. And this is what you would predict if the fracture doesn't deform. However, if you put mechanics into the picture, it turns out that production temperature is going to be a lot lower. Why? Because the fracture is opening more and most of the fluid is just going through the middle and it's not taking any heat. Yeah. Sure. This phenomenon, what we see over here in this plot is what's called plane channeling. And it happens because if you had a fracture, now we're looking at the plane of the fracture, which is this square. If your fluid going from the injector to the producer starts cooling off the rock, the fracture is going to start to open. But it's going to open preferentially in the middle. And as it opens in the middle, because now the hydraulic aperture is larger in the middle, the hydraulic resistance is going to be less in the middle, so you have more and more fluid going through the middle. This is going to become like a highway now for fluid flow, and it's just going to go through there. And because it just goes through there, the efficiency or the effectiveness to take heat from the entire surface is not as good as at the beginning. That's the plane channeling. And actually, let me go straight into the results, because these figures that Matt prepared, I think, are very good for explaining what's going on over here. All right, so here what we have is a two-fracture system. And we're going from left to right as a function of time from 0 to 20 years. And in this case, we're modeling the case of compliant fractures. What that means is that as we change stress, these fractures are going to open significantly, like several millimeters. So what happens is that we start at the beginning, here this temperature, and we are taking heat from the two fracture surfaces. And that's why this is blue, and this is the temperature of the working fluid. So this is low enough so that it's taking heat from the rock. So we're not seeing the rock here, right? The rock is transparent. We're just looking at the fractures. As time passes by, notice that one of the fractures is not taking any fluid anymore. The temperature is not 60 degrees anymore. And not only that, but notice how the temperature now is concentrated a lot less from injector to producer than what it was before. The reason for that is that these fracturings are opening. So let me see if I can zoom in here. So this is the fracture, and now we're seeing at the two faces of the fracture. So actually, my mouse is not following the real time of where I have it over here. So let me do it on the screen. These are the two fracture faces. Most of the opening is in between the injector and producer. Here we're just looking at the bottom half. And the opening is large enough so that most of the fluid goes through the center of the fracture. The entire fracture is this, the entire blueprint. But here it's closed. It's closed here, also closed over there. All of the fluid is going through there. So it's bypassing or short-circuiting our EGS system. And that's not good. That's something that we want to avoid. So now, if we can take a look at that from a point of view of a resistance analogy, where this is our upstream fracture and this is our downstream fracture. Basically, what is going on here is as the fracture opens, the upstream fracture, the fracture is takes more and more fluid, and nothing goes to the downstream fracture because there is more resistance to go through there. And at the end of the day, what we have is that most of the fluid is going to the upstream fracture and nothing goes to the downstream fracture. The severe short circuiting, as you can see in the image, starts more or less after 10 years. So at the beginning, it's okay, but after 10 years, the performance of this enhanced geothermal system is not as good as it was at the beginning. All right, how do we avoid this kind of situation? We don't want short circuiting. We want to make sure that to the degree that we can, we design this system so this doesn't happen. All right. The way that you can avoid this type of short circuiting is by controlling the aperture of the fractures. So this is another case at deeper conditions in which we have stiff fractures. In this case, even if you have a thermal distressing, the thermal distressing is not enough to open the fracture entirely. So always, at every time in this simulation, even though we have a change of temperature, the change of stress is not enough to get the fracture faces to become separated so that the fracture becomes a lot more hydraulically conductive than with the closed faces. So the solution for this is to keep always these fractures under compression. And that will be by managing what is the injection temperature, also by making sure that you don't inject the pressure at the pressure so high that you can also open up the fracture just because of the increase of pressure. So keeping the fracture closed is going to make this short circuiting to be less likely to happen. In some of these cases, it might mean also a lower injection rate. So if you were to analyze this, you could also come up with or try to look for an optimal injection rate. So it's not so small that your power is also very low, but it's also not so high that you get very quickly into short circuiting.
How much can you work short circuit?
Second?
How much can you work short circuit? Like how much? Like you turn up power injection, right?
Yeah. So
Like to what extent? Like, for example, in short circuit, like you have like 20 years.
yeah,
Like can you arrive it in like 30 or 40 years?
I think you could, but that will depend. I cannot give you like an answer in a number because that would depend on the conditions of a particular place, the type of rock, the geometry of the fractures. Something that we didn't talk about here is about also the spacing between the fractures. And there are many variables that go into the analysis of this, but certainly, you know, you have to do a comprehensive study in order to try to avoid that and make sure that, you know, that doesn't happen in the short term, because that will kill your project. Yeah.
How does the depth for this one compare with the, what's the depth for this case?
So in this case, this is just an example. And what we simulated is that at higher depth, if I remember correctly, this was 6 kilometers, the fracture stiffness is a lot higher than the other one that was at 2 kilometers. But here the numbers, you know, are just relative. It will depend on local conditions. Okay, this is a comparison between the shallow and the deep EGS performance. If we have flow channeling and plane channeling, the amount of energy produced here in the y-axis is going to be a lot less than what we compare with stiff fractures and no geomechanics. In this case, our deep system is performing a lot better than the shallow one because the fractures are more compliant in the shallow case. And also you can see the power is quite different in two cases. In this case, we did the comparison also with the same reservoir temperature. So the power comparison is more or less is fair. But we know that deeper locations, the temperature is going to be higher. But this is just to illustrate the effects of how flow channeling and plane channeling can affect an EGS system. And in other solutions, also you could say, well, let's put more fractures. What's going to be the effect of putting more fractures? Well, short circuiting is also expected to happen if the fractures are compliant enough and if the pressures are high enough so that the fractures start to open into significantly large apertures. That's also going to create the short circuiting. And you know, you might have 5 fractures, but just 1 or 2 really producing heat. Another solution for this could be what is called a reverse EGS. Before we were talking about a parallel EGS system in which you have your drilling pad, let's say at this location in the south, and then you inject from the same place, your injector and your producer. However, that has a problem because notice that the shortest path for the fluid to go from the injector to the producer is through the first fracture, or what we call the upstream fracture. So when short circuiting arrives, if it arrives, all the fluid is just going to go to this fracture. You can somehow avoid this if you do this reverse EGS. Now you produce from this location, and what that's going to result in is in a more even distribution of the pressure gradients for all the fractures. But if you're not careful enough, that also can go in short circuit. So you make 10 fractures, and then at the end of the day, just 2 are going to be producing heat. So this can also happen in reverse EGS if the fractures open wide enough to create this short circuiting. Yes.
So I have a question about this slide.
Yeah.
So you try with an intelligent structural system. So right now, in these slides, so you have like full same structure, right?
Yes, correct.
Have you tried with like intelligence and
Yes, we did, because coming back also to the topic we were saying before, that it's very challenging to predict the geometry of fractures. Also, there are no fracture which is the same as another fracture. They are all different. So assuming that all fractures is the same is quite naive. All fractures are going to be different. And we also simulated different fractures. And if we have 2 dissimilar fractures, one larger than the other and therefore more compliant, also that's going to accelerate the short circuit if it happens. So that's not good too for short circuit. So other solutions are to probably this is better seen in this image. If you increase fracture spacing, also you can decrease interaction between the fractures. That also can somehow alleviate this short circuiting. And this is another variable that is explored in this field. Changing the fracture spacing, making larger the fracture spacing is going to change that distribution of fluid fracture in the flow, in the fluid distribution in the fractures, and the well spacing, and also diameter of the well bores that are in the working fluid. That also is going to change the distribution of the fluid in the EGS system. So that's something else to take into account. It's more of a geometrical factors, hydraulic distribution, not much about geomechanics. So let me skip this in this presentation. So stresses are also going to change in these EGS systems. You can also go into past the shear failure line or into the yield line in between the fractures. This could also affect or create, reactivate fractures and create microseismicity that will depend on the orientation of the fractures. and also the magnitude of the changes of the stresses. But this will also affect an EGS system, the same as the closed loop system. So I think this is the last slide I have for my simulations. This is a field which is growing. I don't mean to be pessimistic with some of my analysis, but just to keep this into the picture. And the worst thing would be that we do something and it doesn't work, and then we just quit and say, oh, it didn't work. It didn't work because we saw short circuiting after 2 years, or we saw an earthquake magnitude 5 after 2 years. We need to understand how this is produced and how we can avoid those, or how we can manage them to deploy this technology safely. Because I do believe that this can be done. But this is something new, and we have to study how to do it. And I'm pretty sure that we can do it. And this is an example of the Utah Forge EGS project, where they are actually doing that, and facing all of these problems and trying to solve them. Another example is the EGS project, EGS Colab, where they are also studying the interaction between fractures, how fractures propagate, and also how this happens actually in the field. So we understand these systems better, and we can predict their performance much more confidently than what we can do now. So just as takeaway concepts, geomechanics is important, shouldn't be neglected in geothermal energy. Remember about thermal distressing. That happens when you lower the temperature and you have more rock around you. So the rock is not free to shrink, but instead you have a decrease on the stress, which in some cases it can create or can reactivate fractures, can lead to thermal short circuiting, and both of those which we do not want. And those are also going to affect the performance of a geothermal system in terms of power capacity. So I think, yeah, this is the end. I just want to acknowledge some of the work that we did, and particularly, all the simulations that you saw, numerical simulations, or other than the group from Caltech, were from a grad student, Matt McLean. He has been working very hard on this. And also, if you want to learn more about geomechanics, I encourage you to take my undergraduate class if you are an undergrad, or also my graduate geomechanics class, in which we see these concepts. And actually, they are also on YouTube. I have some videos about thermoelasticity that I go a lot more in detail about some of the things that I have talked today. And if the recording is good too, I'm going to upload this to YouTube for you to watch some other time. So yeah, I think this is it. Thank you guys. And if you have any questions, I can stay as long as you want.